This diagram outlines the exact rule for finding a happy number. Starting with any positive integer, we replace the number with the sum of the squares of its digits. If this process eventually results in a 1, the number is happy. Let's build the engine to do this. Take the number 82. The first step is to separate it into its individual digits, an 8 and a 2. Next, we square each of those isolated digits individually. The 8 becomes 64, and the 2 becomes 4. Finally, we add those two squared values together to get our new target number, 68. That exact three-step process, separate, square, and sum, must run continuously on every new number we generate. This progression maps the first state, the successful path. If we start with 19, the math engine outputs 82, then 68, then 100, and finally lands perfectly on 1. Since we hit 1, 19 is a happy number. But we need to look at what happens if we plug the number 2 into our engine. The number 2 transforms into 4, then 16, 37, 58, 89, 145, 42, 20, and then right back to 4. It falls into an inescapable repeating 8-number sequence. If we don't code a specific exit condition into our algorithm, this loop will run infinitely and crash the program. This box outlines the most intuitive, brute force way to handle the problem, using a hash set. We store a history of every number we've seen, immediately checking each new sum to see if we've recorded it before. If we run our happy number, 19, the hash set passively records the sequence until the engine successfully reaches 1 without issue. But if we run the unhappy number, 2, the set fills up with the sequence up to 20. Then, when the engine calculates a 4 again, the hash set flags the duplicate and triggers a cycle alert. This approach works, but it has a fatal flaw. Because the memory usage grows indefinitely with every step the engine takes, it requires big O of n space. The challenge is to engineer a way to achieve this exact same cycle detection without relying on a massive memory-hogging historical record. The optimal solution is Floyd's cycle detection, often called the tortoise and hare method. This allows us to track the numbers using strict constant space. Instead of storing a history, we create two separate pointers. The slow pointer, our tortoise, applies the math transformation exactly once per iteration. At the exact same time, the fast pointer, our hare, applies the exact same transformation twice per iteration. When two objects move at vastly different speeds inside a continuous loop, they will inevitably interact and collide. The tortoise and hare method achieved the exact same cycle detection strictly within big O of 1 constant space.
So initially, I create a function called square sum, which takes n as its input. Inside this function, I create a variable called sum and initialize it to 0. Then I run a while loop as long as n is greater than 0. In every iteration, I take the last digit of n, square that digit, and add it to sum. After that, I remove the last digit from n by dividing it by 10. This process continues until all the digits are processed. Finally, I return the value of sum. Now in the main function, I create two pointers called slow and fast, and I initialize both of them with n. Next, I use a do-while loop. First, I update the slow pointer by calling the square sum function once. Then, I update the fast pointer by calling the square sum function 2 times. Since the fast pointer moves 2 steps at a time, it behaves like a fast pointer in the cycle detection algorithm. This process continues until the slow pointer becomes equal to the fast pointer. When both pointers become equal, there are only 2 possible cases. If both pointers become 1, it means the number is a happy number, so we return true. Otherwise, if they meet at any other number, it means a cycle has been detected, so we return false.